Hello everyone, now I will present our work on Dependency-Aware Neural Architecture Search, DANAS. This work is a collaboration between East China Normal University and Aalborg University. Neural Architecture Search, NAS, reduces the burden of manual design by automatically building neural network architectures. Among NAS approaches, differential methods such as DARTs have gained popularity due to their search efficiency. Despite achieving promising performance, the DARTs series still suffers from two major issues. 1. It does not explicitly establish dependencies between edges, which may lead to suboptimal performance. 2. The high degree of parameter sharing results in inaccurate performance evaluation of subnets. To address these issues, we propose to explicitly model the dependencies between different edges to construct a high-performance architecture distribution. Specifically, we model the architecture distribution in DARTs as a multivariate normal distribution with a learnable mean vector and a correlation matrix, which represent the base architecture weights of each edge and the dependencies between different edges, respectively. With the learned dependencies, we dynamically prune the search space to mitigate inaccurate evaluations by only sharing weights among high-performance architectures. Additionally, we identify effective motifs by analyzing the learned dependencies, guiding human experts to manually design high-performance neural architectures. In more detail, we model the architecture distribution as a multivariate normal distribution with a learnable mean vector and correlation matrix, where the mean vector represents the base architecture weights of each edge and the correlation matrix captures the dependencies between different edges. Our overall training process is as follows. At each optimization step, we sample the architecture weights from the distribution and train the supernet using gradient descent. Since the architecture weights of the supernet are sampled from the architecture distribution and are directly influenced by the learnable correlation matrix, we can explicitly model edge dependencies during the forward pass of supernet training. Unlike DARTs, which overlooks edge dependencies during the forward pass, our approach enforces explicit constraints on architecture weights. This strategy prevents the exploration of suboptimal regions in the search space, ultimately improving the efficiency of differentiable NAS algorithms. The NAS Bench 201 is a tabular cell-based search space that consists of 15,625 possible architectures. Table presents the performance of our proposed method in the NAS Bench 201 search space compared to other state-of-the-art methods. Our approach significantly surpasses both the first and second-order DARTs baselines. Compared to the SOTA algorithm, we achieved better performance, demonstrating the effectiveness of our algorithm. To demonstrate the transferability of DANAS, we also conducted experiments on the large-scale ImageNet dataset. We trained the architecture for 250 epochs using a batch size of 1024. As shown in table, compared to other methods, DANAS achieved competitive results. We ran these different ablation models multiple times on the NAS Bench 201 search space and reported the average results. Figure shows the accuracy of these four ablation models on the test set for SAFAR 10, SAFAR 100, and ImageNet 16-120 as search time progresses. We observed that full achieves the best and most stable results. For mask 30% and mask 60%, compared to full, the part of modeling the dependencies between edges in the search space is missing. This leads to an inability to provide sufficient constraints to explore the search space, making it easy to fall into local optima. The diagonal model does not establish any dependencies between edges, which results in common performance degradation over time. This demonstrates that the proposed dependencies between operations are beneficial for both algorithm stability and performance improvement. In conclusion, this paper introduces DANAS, a novel approach that explicitly establishes dependencies between edges in the search space of neural architectures. Unlike traditional methods that rely solely on implicit modeling, DANAS leverages both implicit and explicit modeling to capture more comprehensive inter-edge dependencies. Furthermore, the use of the learned dependency matrix allows for dynamic pruning of the search space, addressing the issue of undesired co-adaptation. Extensive experiments on real datasets provide strong evidence of the effectiveness of the proposed method.